Every bridge, every railway track, every skyscraper, every pressure vessel, every stainless steel kitchen, and every heavy machine has one hidden ingredient that most people never see. It is not pure iron. It is not coal. It is not limestone. It is ferroalloy, the powerful alloying material that gives steel its strength, hardness, corrosion resistance, toughness, and performance. A ferroalloy is basically an alloy of iron with another important element such as manganese, chromium, silicon, molybdenum, vanadium, titanium, or nickel. In steel plants, ferroalloys are used to introduce these elements into molten steel in a controlled and economical way. The US EPA defines ferroalloy as an iron alloy used to carry another element into molten metal, usually during steel manufacture. Without ferroalloys, modern steel would be weak, unstable, and limited. The story of ferroalloys begins with the story of steel. Ancient blacksmiths could make iron tools, but they did not fully understand chemistry. Some steels became hard. Some became brittle. Some rusted quickly. Some survived for generations. The real revolution came in the 19th and early 20th century, when scientists and engineers discovered that small additions of elements like manganese, chromium, and silicon could completely change the behavior of steel. Manganese helped remove sulfur and oxygen from steel. Chromium created corrosion resistance. Silicon acted as a strong deoxidizer. Vanadium and molybdenum improved strength at high temperature. As demand for alloy steels and deoxidizing agents increased in the early 20th century, the development of the submerged arc furnace became a major breakthrough in ferroalloy manufacturing. Visual suggestion: old blacksmith furnace, early steel mill, electric arc furnace, modern ferroalloy plant. Steel is not just iron and carbon. Real industrial steel is a carefully designed chemical system. The principal ferroalloys are based mainly on manganese, chromium, and silicon. According to the U.S. Geological Survey, manganese is essential in virtually all steels because it helps neutralize sulfur and acts as an alloying element, while chromium gives stainless steel its corrosion resistance. Let us understand with simple examples. Ferromanganese is used for deoxidation, desulfurization, and strength. Silicomanganese adds both silicon and manganese. Ferrochrome is the backbone of stainless steel. Ferrosilicon removes oxygen from molten steel and improves magnetic properties. Ferrovanadium improves high-strength steel. Ferromolybdenum improves heat resistance and creep strength. In manganese specifically, steelmaking accounts for around 85% to 90% of manganese demand, and manganese ferroalloys are the main way this element is added to steel. So ferroalloys are not ordinary raw materials. They are the vitamins of steel, added in small quantities, but responsible for huge changes in performance. Before entering the plant, we must know what is being manufactured. 1. Ferromanganese, FeMN, used in carbon steel, structural steel, rails, and plates. It helps remove sulfur and oxygen and improves hardness. 2. Silicomanganese, CMN, contains manganese and silicon. It is widely used as a deoxidizer and alloying material in steelmaking. 3. Ferrosilicon, Fe, made from quartz, iron source, and carbon. It is used for deoxidation and in electrical steels. 4. Ferrochrome, Fe, produced from chromite ore. It is essential for stainless steel production. 5. Special ferroalloys. These include ferrovanadium, ferromolybdenum, ferrotitanium, ferroboron, and ferroniobium. They are used in high-performance steels, tool steels, aerospace alloys, and heat-resistant materials. A ferroalloy plant begins with 4 main raw material groups. 1. Ore. This is the source of the alloying element.
For ferromanganèse, the ore is manganese ore.
For ferrochrome, the ore is chromite. For ferrosilicon, the source is quartz or silica. For ferromolybdenum, the source is roasted molybdenum concentrate. 2. Carbon reductant. Carbon is used to remove oxygen from metal oxides. Common reductants include coke, coal, charcoal, and sometimes low-ash carbon materials. 3. Iron source. Iron is needed because ferroalloy is an iron-based alloy. This can come from iron ore, mill scale, steel strength, or iron chips. 4. Flux. Flux controls slag chemistry. Limestone, dolomite, quartzite, or other fluxes may be used depending on the alloy. In simple words, the recipe is: or plus carbon plus iron source plus flux plus electricity equals ferroalloy plus slag plus gas. The process does not start inside the furnace. It starts in the raw material yard. The ore is first received, tested, crushed, screened, and stored. Correct size is very important. If the material is too fine, gas cannot escape properly. If it is too large, reduction becomes slow. If moisture is high, furnace stability becomes poor. So the plant carefully controls moisture, particle size, chemical composition, fixed carbon ash content, phosphorus, sulfur, silica, alumina. Basicity in modern plants. Raw materials move through conveyors, hoppers, vibrating feeders, magnetic separators, and weighing systems before reaching the furnace.
The most important equipment in bulk ferroalloy manufacturing is the submerged arc furnace, also called SAF. Most bulk ferroalloys are produced either by carbon reduction in a submerged arc furnace or by metallothermic reduction using metals like aluminum or silicon for special low-carbon alloys. In a submerged arc furnace, large carbon electrodes go deep into the raw material charge. These electrodes carry huge electrical current. Unlike an open electric arc furnace, the arc is hidden below the charge. That is why it is called submerged arc. The heat comes from two sources: electrical resistance of the charge, and arc and microarc heating near the electrode tips. Temperatures inside the reaction zone can exceed 1,500 degrees Celsius, and for silicon processes, temperatures above 1,800 degrees Celsius may be required. Inside the furnace, the process is a battle between oxygen and carbon. Most ores are oxides. Manganese ore contains manganese oxides. Chromite contains chromium oxide and iron oxide. Quartz contains silicon dioxide. Carbon removes oxygen from these oxides and forms carbon monoxide gas. The simplified reaction looks like this. Metal oxide plus carbon results in metal and carbon monoxide. For ferrochrome, Cr2O3 plus 3, C results in 2Cr plus 3Co. For ferrosilicon, SiO2 plus 2C results in Si plus 2Co. For manganese, MnO plus C results in Mn plus Co. These are simplified reactions. In real furnaces, the chemistry happens through many intermediate stages: slag reactions, gas reactions, and metal-slag equilibrium. As the ore is reduced, molten alloy droplets form. These droplets travel downward and collect at the bottom of the furnace. Above the molten alloy, slag floats because it is lighter. So inside the furnace, two liquid layers are formed. The top layer is slag, and the bottom layer is molten ferroalloy.
A ferroalloy furnace looks simple from outside, but it is one of the most difficult industrial furnaces to control. Operators continuously monitor electrode position, current, voltage, power factor, furnace load, burden level, gas pressure, tap temperature, slag fluidity, metal chemistry. The electrode must neither go too deep nor remain too high. If the electrode is too high, arcing becomes unstable. If it is too deep, power distribution becomes poor. If the charge is too tight, gas cannot escape. If the charge is too loose, energy loss increases. The furnace is fed continuously or semi-continuously from the top, but tapping happens periodically from the tap hole. In large ferroalloy furnaces, power demand is extremely high. For example, high-carbon ferrochrome production may consume around 3,300 to 3,400 kilowatt-hours per ton of metal, and power cost can form a major part of total production cost. Ferrosilicon is even more energy-intensive. Published studies report energy consumption for 75% ferrosilicon in the range of 8,000 to 11,000 kilowatt-hours per ton. That means ferroalloy manufacturing is not just metallurgy. It is also power engineering, heat transfer, chemical reaction engineering, and process control, all working together. After enough metal has collected at the bottom, the furnace is ready for tapping. A tap hole is opened using oxygen lancing, drilling, or mechanical tapping equipment. Suddenly, a bright orange stream of molten ferroalloy flows out. The temperature is extremely high. The light is intense. The sound is powerful. Molten metal and slag flow into ladle or runner system. Since slag is lighter, it can be separated from the metal. This is one of the most dangerous and critical stages of the plant. Operators must control tap hole opening, metal flow rate, slag metal separation, ladle position, splashing, fume extraction, personal safety.
After tapping, the molten ferroalloy must be solidified. Depending on plant design, the alloy may be cast into sand beds or cast iron molds. It can also be processed in chill molds, continuous casting beds, or granulation systems. As the metal cools, it changes from a glowing liquid into hard alloy lumps. The cooling rate affects cracking, lump size, and handling behavior. For some alloys, controlled cooling is important to avoid excessive fines generation during crushing. Steel plants do not buy ferroalloy as one giant block. They require controlled size fractions. After cooling, the alloy is broken by hydraulic breakers, jaw crushers, cone crushers, or roll crushers. Then it passes through vibrating screens. Typical commercial sizes include various ranges from 100 millimeters down to fines below 3 millimeters. The final size depends on customer requirement and steelmaking practice. Correct size is very important because ferroalloy must dissolve quickly and uniformly in molten steel. Too large, and it dissolves slowly. Too fine, and it can oxidize or get lost in slag. Every batch of ferroalloy is tested before dispatch. The laboratory checks element percentages, moisture, size distribution, and bulk density. Ferrochrome is checked for chromium and impurities, while ferromanganese is checked for manganese. Ferrosilicon is checked mainly for silicon, aluminum, calcium, carbon, and phosphorus. Quality control is critical because even a small chemistry error can disturb steelmaking. Precise chemistry prevents brittleness and ensures efficient deoxidation in the final steel product.
Ferroalloy manufacturing produces heat, dust, fumes, carbon monoxide, slag, and high electrical load. Modern plants use several environmental control systems: bag filters, fume extraction hoods, gas cleaning plants, water-cooled ducts, slag handling systems, dust recycling, waste heat recovery, closed or semi-closed furnaces. High-carbon ferrochrome production is energy and emission-intensive. One study estimated energy requirements between 40 and 59 GJ per ton of ferrochrome, depending on route and technology, and showed that closed furnaces, preheating, pre-reduction, and cleaner electricity can reduce emissions significantly. Let us summarize the entire manufacturing process in one clear flow. Raw material selection, crushing and screening, weighing and batching, charging into submerged arc furnace, electrical heating and reduction, formation of molten alloy and slag, tapping, slag separation, casting, cooling, crushing, screening, chemical testing, packing and dispatch. Ferroalloy may not be visible in the final steel product, but its impact is everywhere. It is inside the stainless steel that resists rust, inside the rail that carries heavy trains, inside the crane hook that lifts massive loads, inside the turbine shaft that survives high stress, inside the automobile steel that must be strong and formable. A few kilograms of ferroalloy can change the destiny of tons of steel. That is the power of metallurgy. From raw ore to electric furnace, from molten metal to alloy lumps, ferroalloy manufacturing is one of the most fascinating combinations of chemistry, electricity, heat, and industrial engineering.